Okay, so common mistakes in small-size biological experiments and how to avoid them. Now, what I would like to do is make this interactive, because I don't like what I call a frontal assault, because you have all cholesterol-induced coma right now, and I'm not sure that statistics is a right subject to get you out of that one. Okay. First of all, my background. Since May 1st, I'm the director of the Statistical Consulting Unit at University of Florida. One thing of that is it is a service unit. Just like the university provides power, office space, water, we are part of the infrastructure. And that was very important to me when I interviewed there. And I got this approved all the way from my colleagues in the department, all the way to the VP for Natural Resources, Ag and Natural Resources, Jack. So, as said, service unit, and our services are available free of charge to anyone who has any relationship to IFAS. So from a county agent all the way to the VP for Ag. If you have a relationship, we are for you available. Our services are available. I have 2 full-time staff members, 2 PhD, 1 PhD level and 1 master's level, and they're really good. What we are, of course, concerned is we are what I would call the statistic analysis value chain. We are, our job starts routinely when we get the raw data, and in the end we have the formatted output. Problem is, of course, where a lot of researchers fall flat, and students in particular, they do not check their data. It drives me nuts sometimes. And it takes me, I think my record is about 30 seconds after they walk into my office that I discover that the data, something is wrong. And in teaching, and you too need to learn it, the data has to make biological sense. I use an example. If you have 160 bushel per acre corn yield in central Alabama under dryland condition, it is possible, but it's not likely. Now, if you take that experiment in Ames, Iowa, in that county, they haven't had an average yield less than 160 bushels per acre, I don't know, for probably the last 20 years. So it's highly probable. So it's actually an approach of Bayesian, actually. If you know the classical explanation of Bayesian, if you want to find an elephant, it would help to know if there's a likelihood of actually finding one. So if you go to Antarctica, probably is hard to find. In the US, you can do it, but it's hard. But if you go to India, that likelihood increases. So that's prior knowledge. That's what it's all about. Interesting fact is, you know about the Cherokee. Since in North Carolina, Sequoia developed a written syllabary for them, a pictorial language. And interesting stuff, and that was the connection to elephants. The symbol for elephant and butterfly is the same. Why do you think that is? Yes, you do.
There's no possibility to be confused on solutions.
That's for one thing. There are no so the meaning derives from the context. The second, what's the common thing? If you look at an elephant from the front and you looked at a butterfly, that's right. It's the ears. I thought it was genius when I first heard it. I said, that guy was really good. And Sequoia was a unusual, really unusual individual. Has really nothing to do with it, but it's context and the subject-specific knowledge that you as researchers or in the development bring to the process. And statistics is not a crutch, it's a tool. And I think that should have been clear from all the presentations this morning. It is a tool, but you bring your subject-specific knowledge for them. Now, when you do an experiment, this is what happens. We have a population, and a population is anything you define it to be. But you don't know. You don't know the 2 critical statistics, measure of central tendency and measure of dispersion. We don't know about it. We have to estimate that from the data. And you take a sample, and based on that sample, you draw a conclusion about the population. That's all that's happened. It's not limited to sampling marbles. It is what you do in an experiment. And sometimes it's not a good sample. Now, there's one person in this room there who can understand what I'm saying, the analogy. Sometimes it's like playing cards. You would call it ein Griff ins Klo. It's when you really play cards and you get a really bad hand. The translation is you reach into the commode. You know, when you do that, it's not going to come out clean. And that happens in sampling. Now, what we're trying to do, make everything possible that our sampling is good. So, for example, if you do insect sampling, you make sure that you don't sample the edges of your plot because it changes. You do uniform sampling procedure. That's why we set up sampling procedure. But this is in essence what you're doing in experimental research. You're taking samples. Okay, now let me switch to our data. So what we did here is we let's see, where's my there. Okay, so I asked you to take a sample of 10 out of the marbles. The marbles, you had 6 different colors, and you just simply noted the color. Now, that's a prime example of a variable that has a binomial distribution. It's a proportion. And something that didn't come up this morning is actually when you take data, the type of variable that you're interested in will tell you something about a likely probability distribution that underlies it. So if you are taking proportions, it is unlikely that those proportions will be normally distributed. They are proportions. And what distinguishes a proportion from a normal, so a binomial from a normal random variable, is that in the binomial there is a relationship between the mean and the variance. The minute you have the location estimator, p hat, you know the variance because it's p times 1 minus p. That's a big problem that weed scientists face when they do weed efficiency rating on a scale of 0 to 100. It's basically a proportional rating. It's a pseudo-binomial. And that's why they have problems, why weed science data make really nice. I like to beat up on weed scientists in class. They know it because it's so easy. The nature of the field implies that they're going to have problems with their data. That's why they have this infamous or famous arcsine square root transformation, because it works reasonably well. Now, we don't have to do that anymore. We have a lot of other tools nowadays. So the data tells you, so if you do counts, it's unlikely, unless you have lots of counts going into a particular mean, then you may capitalize on the central limit theorem. But the underlying assumption that the counts have a Poisson distribution, and the Poisson means the variance rises proportionally to the mean. The larger the mean, the larger the variance. The beauty of the normal is, and that's why he called it Gaussian. Statisticians don't like the term normal. They call it Gaussian distribution after the German mathematician who was enshrined on the old 10-mark bill. But we've known about it for a long time. What's the normal case is it's actually one of many cases. It's not normal in terms of the meaning of normal has nothing to do with normal versus non-normal. It's the general, like we talk about normal temperatures, they are long-term averages. Well, most of the data actually are not, don't fall in that category. And in the past, what people did is they made the data fit their preconceived notions. And we're moving away from that. So let's talk about the binomials. So we have for each of the parts, we have 5 replicates. And this is where I like this little program put out by the SAS company. We can do histograms. Okay, so these are. Let me just change the. Okay. So what we have is with the overall the probability is doesn't look like a normal. Which one of these would you say, for which one of the colors do we have a distribution that might be normal?
Yellow.
That's precisely because the other ones I manipulated. The yellow I didn't. So you can tell, just looking at the data, and that was the point that was made this morning. Look at your data. The first line of defense is look at the data. And so if I had calculated proportions, and well, this is automatic, so you can't happen, but if your data are proportions and you have a number that's larger than 1 or less than 0, you have a problem in your data. And you need to fix those problems before you do that. But it's highly variable. See, we have a lot of them, and I need to, well, I didn't bring my, yeah, I think here for black, yeah, that's right. It's black and green are interchanged. This one actually has more, the first population actually has more black. And so if I did this by populations, it would pick up. The only one that it didn't manipulate was yellow. So this is like what you're doing in a real experiment. You have a cloud, if you will, of unknown responses. And you are taking a random sample. It is just a snapshot. Don't let me slip into my German here with my accent. I have still have a fairly heavy accent after 40 years, but talking to a German tends to reinforce that. So stop it, Stefan. No, actually I like it. Even though he's from an area where they can do everything expect speak high German. But it's nice. I love Swabians. They're great. Or as one of the political candidates says, many of my friends are Swabian. So that's this whole exercise was to drive home the point that you actually have a sample. That's what you're doing, and you're trying to estimate an underlying population parameter. Okay, there we go. So now let me share some tales from the dark side. I am the member of the National Grass Variety Review Board for the Association of Official Seed Certifying Agencies. The long organization was a short name. And so we meet once a year to approve varieties that are approved for certified seed production in Oregon. And the technician who goes out to field actually has to have an idea what this variety looked like. Now, this is not like corn or wheat. Corn as an F1 hybrid, everything is uniform. What you see is environmental variation, similar with wheat. Wheat is a highly self-pollinated crop, or soybean would be the same thing. Well, these grasses are highly outcrossing. Basically, you can assume that every plant in that population has a different genotype. This was a statement they made. 30 plants showing the typical characteristic of the experimentals were measured. You have to measure at least 30 plants. So that's what people do. They measure 30 plants. So what does that mean? That means they went in there and said, okay, this is what I want it to look like, this one looks like, and this one looks like. I'm going to measure those plants. The problem is no statistics can salvage you. Statistics is based on the assumption that it is a random sample. That's why I didn't want you to look in there and say, I like the green ones. Or since I'm red-green blind, I can't tell the difference. So, but those two colors will be preferably chosen. No, you can't do that. It is a random sample. Now, what's not random is the treatments that you apply. In this case, they were this experimental variety plus some check varieties. So that's one example. So speak up if you have a question anytime. Now read this, and I'll give you a couple minutes. Do we have any water or anything out there? I would love to have some water. So, give you. Okay, so what they did is they wanted the objective of the paper. They wanted to use composting to reduce odor and improve fertilizer value of some hog manure. So what they did is they got a batch of manure from a single hog house and did 3 composting treatments. They had none, the method 1 and method 2. Now they did this in a pile, mixed thoroughly, and they got that. Thank you. And so then after they did that, they took about 10 samples of 300 from random spots in each pile, did the analysis, and then they concluded something about the differences among these 3 treatments. So let me ask you a question. What's wrong with this picture? Or is there anything wrong with it? Maybe not.
How do we know that they were actually random spots in the pile?
Okay.
Just because they say so?
Yeah. But we assume that. But that would be one. But what's the problem?
Well, it's a single batch of manure from a single population of hogs.
Yes, and if these had been from bovines, you said it was a whole bunch of BS, this paper. Yeah, what they're trying to do is they're trying to assess the differences among these treatments, but the treatments are not replicated. They just sampled, and so what they're actually the pooled variation is actually laboratory error and sampling, combined error of the sampling, and this is where your point comes in. That would show up they may have an edge effect there, and the laboratory precision. But that's not the measure. That's not what you need. You need an appropriate error term for that. So this one, the other one, I said, yeah. And these are actual papers that I reviewed, and I could not make this up. I don't have enough imagination to make this up. Now, some people, yeah. So that's why I'll never be a novelist, because I just don't have enough imagination. So what these guys did is they had a beautifully designed experiment. They had 9 blocks, so it was an RCB experiment, 9 treatments, so they had 81 experimental units, and the response variable was related to soil. So what they did is what we commonly do in soil science. You have a plot, and then you take a whole bunch of samples, then you make a composite, mix it, and that will represent that plot. So, yeah, within a plot.
Okay.
Because there's variation. I mean, if you do field research, you have an assumption there is spatial variability. So to avoid that, they took, I think, from these, they had 50 cores. So they did a beautiful job. And then, so they mixed them thoroughly, and then had derived a sample about 250 grams. That's all we need for soil analysis. And so they had 81 samples. Then they ran into a problem because they ran out of money. So, and they made a rash decision, and you shouldn't. If you're contemplating that, is grab that cup of coffee, or if you're inclined, grab that beer. Think about it. Should I really do this? And in most cases, the answer is no, you shouldn't. So what they did is they lined them all up by treatment, and then pooled all the samples for a given treatment. And so they sent these samples to the lab. They did them in duplicate, and then they compared the treatment means using the pooled among replicate variation as the error term. I said I cried when I read this paper, because it was a beautifully designed experiment, and they could have done it differently. What should they have done? If they only had money to do 18 samples, what should they have done? They should have picked 2 reps at random. Or they could, 2 reps at random. That would have been save the other soil samples. Maybe down the road, if you couldn't detect the significant treatments, maybe down the road you have another chance of getting some money. But they spend all, and this cocoa trees. I mean, it takes a long time to get the data. And with a single rash decision, they negated all the stuff that they did. I said, I cried when I heard, and these are not made up data. People tend to assume they are made up data. No. So another thing, so don't do that. The other thing is I called armed and dangerous. I have to apologize to John Candy. Rest his soul may rest in peace. This is probably what your friends from Syngenta were responsible for. I'm not sure, but one of the big companies, one of the big customers for ARM stands for those of you who doesn't know ARM in this room? Agricultural Research Manager. It started off as weed manager and then pesticide research manager. Now it's ARM, Agricultural Research Manager. It's basically a experimental design tool and a data management tool to which they added some fixed effects analysis at the end. But one of the things that one of the big customers insisted on is that they represent the first rep in a non-randomized fashion because they want to use it for field days. And so you can go through it. You can go by treatment number and so on. What's the problem? Well, if your treatment list would be random, would be that would be as good a randomization as anything else. However, it's not, because they use some time-saving tools to enter data. You would do the same thing. So let's say you have a experiment with 2 herbicides and 3 rates, maybe half X, 1X, and a 1.5X. So what you do is, and ARM recognize that. So you enter the first herbicide or pull it down from a list. I don't know, haven't worked with ARM in a while. And then you just fill in the rates, pull in the other herbicide and pull in the rates. So you have 6 treatments. Now when you don't randomize it, the first one looks like a split block. You have on one side of the block, you have herbicide 1, other side of a block, and then you have the rates in order. So there are 2 consequences. Let's assume you have a gradient in the field, and your best treatment will be your best treatment that we expect the best response will also be on your best plot. You will overestimate the real treatment differences. And we call that a really type 1 error rate. Or the other way around, you will compress the treatment difference so you have lack of power. Now, if you had 100 reps, probably wouldn't matter all that much. However, we don't. We heard this morning, standard agronomic experiment has 4 reps, right? Can you tell me where that comes from? I don't think it's written anywhere. Yeah, but it happens when you talk to people, said how many reps does an agronomic experiment have to have? They say 4. I said, why? And there's no answer. People also seem to think that the blocks have to be contiguous. So if you have a field, the blocks are nicely, however they are arranged. Nowhere. If you go back to Fisher's early work, that's the antithesis of what he was trying to do. He was trying to block on an environmental factor. And his famous experiment was that they had a windbreak there. So you had protection from the wind, and as you went farther away, there was more exposed to wind. There's no indication that they should be contiguous. In fact, you're probably better off putting them on vastly different places. You get much more information out of it. But that's not what I have done. Walt Stroop, my colleague at Nebraska, calls this convenience blocking, or half field will travel. Now, a lot of field managers, if you have a station manager, that's the way they like it because it enables them to plan. If you come to your station manager and say, I would like to block there, say, hey, did you have too much to drink last night, or what's wrong with you? But that's the way we really should do it.
Richard, I just give you why 4. I know the 4 is not enough. But why cannot afford the number of 4? Europe, I think, work with like GM, genetically modified traits. For Europe, Food Safety Agency, this is basically EU EFSA, I mean, like
Yeah.
equivalent to FDA, USDA.
Yeah,
here.
yeah, I know.
So
about it.
they're required when you do the environmental risk assessment, food risk assessment, you need minimum 4
Yeah.
good repeats.
But
If
this-
anything less than 4, that trial they don't count.
Yeah.
Yeah.
But this 4 predates EFSA way
no,
back.
actually, no.
Oh
no,
yeah.
Actually, no. EFSA. I mean, if you look at the EFSA deregulation documents, see there, they said you need any trial, you need an added repeat, added location, minimum added location. Each location must have 4 valid repeats. Anything less than that,
Yeah.
if you miss one, you're done. This
Yeah,
location
but
doesn't
what I'm
count.
trying to tell you is that magic number 4 predates EFSA. It goes way beyond that. So
Okay, I just
yeah, yeah. I mean, it appeared. Some of you made little experiment. What is it? Experimental plot design. Something that spiral bound applied book that some of us remember. All right. Yes.
Doesn't that N equal 4 get you like 80% of the way to having your?
Doesn't
Doesn't it get you closer to the central limit theorem being a valid assumption or a valid tool?
Yeah,
for
what
your
happens
distribution?
actually, you are almost at the break point for your serve. But there's no magic number. It actually depends on your objective.
Sure.
And if you had the option, if I did an experiment, if I had the option between putting 4 reps at one location or 2 reps at 2 locations, I would choose the latter. Actually, I would probably put 1 rep at 4 locations. You got a lot more information that's usable. Now, you may get horrible CVs. You may get horrible, but CVs are overrated anyway. You may get large standard errors, but you get the information. It actually goes back to the talk: is get away from those darn p-values and look at the information that you're doing. Now this is the long and I call it the long and skinny. So this one experiment at Hastings in Florida. A student came to me, said we got this irrigation rep, and they are actually producing chipping potatoes in Florida. I didn't know that. And so they had irrigation, and then they had 12 plots, which was actually 11 originally, a combination of fertilizer source, either drip irrigation or dry, and then timing. And this is what he proposed. So this is about 600 feet from one end to the other. So each block was then one of these beds. And I looked at him and I said, he is a student, so I used somewhat mild language. I said, the environmental variation, the spatial variation here is going to eat you up. You are not going to detect any differences, no matter how hard you try. You've got to reduce the block size. As I said, he had 11. Looking at it took me a little while, and I realized, look, if I added another plot, I can make a 3x4 factorial. I have 4 here, and I put the other factor here. So I could create a split block design. So you have blocking in addition to reps, you have blocking in 2 directions, 2 main plots. And the emphasis is where you want it to be actually in that design. The emphasis is on the interaction. That's where you want it to be. And so we reduced the block size here from about 50 by 600 feet to about 120 by 200 feet. So much better design. Now I can't guarantee you that he is going to detect significant differences or whatever you want to call it, but he's going to have a much better chance. And they're going to do this for 3 years, so he has that environmental replication. But his chances of success are much better. Now, again, this is straight from Wikipedia, our internet textbook in these days. But so this is what we are doing. We want to do. We have experimental research with random assignments. In social sciences, they often do this correlation study, and that's the problem. You have correlations there. Sometimes in ecology, you do the semi-experimental one, but this is where we want to be. We want to be experimental. We want to apply treatments deliberately. And because we are interested in causal relationship, even though casual is very closely related to causal, I mean, same letters, but it's a different concept. Often in literature, you see casual relationship, and that's just a typo. Happened. So what does that mean? If we want to see a change in the response, we've got to make sure that we see a change. We have to apply something. That's why it's experimental research, sometimes called, what other term they call, intervention or whatever. And what you have here is this ceteris paribus principle. All other things being equal, we're trying to exclude all the other ones, all the other influences. Now, farmers like to see large plot research. We like to do small research, and precisely for this reason, we are not interested in the big picture. We're trying to isolate a specific phenomenon, and so we're trying to get rid of all the confounding influences. Now, R.A. Fisher was mentioned. If you get the musical reference here, I'll buy you a beer tonight. You get the musical reference? Anyone? No?
Okay.
It's actually Handel.
Okay.
It's a Detting Te Deum. It's from Psalm 31, the text. I just replaced God with R.A. Fisher. Well, for many people he was. And that guy was phenomenal. Now, when you do experimental research, you have to know some basic definition. That's just a tool of the trade. I mean, you can't be a car mechanic and not know what a fuel injector is. If you have, describe that thing that squirts gasoline into that cylinder, that makes communication very hard. So same in this. You have experimental design. What experiment? Critical is the definition of experimental error, and experimental unit and associated experimental error, and sampling and unit and sampling error. And the confusion that those two tales from the dark side suffered because they didn't know the difference. Now, when I teach, I hammer my students with that, and it's strict indoctrination. I don't care what it has nothing to do with modern teaching techniques. I said, this is you have to remember. And I test it, and they get tired of it, they get grumpy. But the best of my students, finally, they remember, they internalize it, and that's what you have to do. Experimental design is a process. It's not just, now do I do the randomization? There's much more to it. It's planning the entire experiment. Then the conduct is not separate from the plan that you have, and the analysis has to follow the plan. Well, the battle cry of consulting statistician is analyze them as you randomize them. So if you use one design, that has consequences for the analysis. So in experimental design, what we have a treatment structure, and the randomization scheme that we're using relates that treatment structure to the design structure. Now, when you deal with gene jockeys, lab folks, and so on, they really don't know this part, even though they could profit from it. But it hasn't been part of their training. So, conditions for a valid experiment: we need to have replication, and that means you have to have treatments applied to experimental units independently. Now, sampling 5 plants out of a corn row that's sampling, but that's not replication. But you can think of it, the variation among these experimental units treated alike, which is the definition of experimental error, that is a noise against we evaluate that signal. So doing an experiment that's like signal and noise. How many of you are public radio listeners? You can admit to it, I know. You can. So what happens? Well, the signal is only valid in a certain range, right? And then you probably pick up a religious broadcaster or some right of center. Right of center talk show, which tend to have strong signals. Well, so you lose the noise. If you like to music, that line between being annoying and enjoying and being annoyed is very, very narrow. So think of your experiment, your data, that you're trying to tease out that signal, and you ought to do everything possible to enable yourself to pull out that signal, and then compare that to the noise. And when that signal exceeds that noise, then you've got something. If the signal is all noise, that's all it is. Now, there are other techniques. See if these Bayesian networks may be able to extract some signal out of some really, really noisy data. Randomization is the other one. It's the independent assignment of treatments. Some of may know George Casella, one of my predecessors in Florida, who unfortunately died at a very young age. In his textbook, he lists the following benefits, and this is the one that's often mentioned first. It's the elimination of systematic bias. It doesn't eliminate the bias, it's just that it doesn't unduly influence one treatment. And one of the terms you may hear is confounding variables, or if you deal with someone who was trained in Britain, they may call it a lurking variable. That's one of my instructors, he called about lurking variables, make it sound real ominous, which it is because you don't know about it. Then you want a representative sample. That's why you didn't look and you shook it in between. You want a representative sample. In this case, we sampled with replacement because the numbers is too small. The probabilities would have changed if you had sampled them all at once. And even if we don't know these unconfounding variables, we can account for them. Now, anything you can do to account for those variables. Now, by any means, if somebody drove a tractor through your experiment or whatever, yeah, you need to take some data on that. Now, whether or not your grandma didn't have a very good day when you harvested the field experiment probably is not relevant. But if in doubt, I would take more observations or more notes than fewer. You can always disregard them. But if you don't have, and then you scratch your head, now, what did I do in this one? What order did we process them? When you do experimental research, it helps to be mindful of the presence of Murphy, because Murphy is always there. Whether you like him or not, he is there. If it can go wrong, it will go wrong. And what really the hallmark of a good researcher is anticipating what can go wrong. And it also has to do with personnel and human interactions. What you always want to do in whatever research group you have, you want to have a climate of openness, that people feel comfortable with admitting they made a mistake. And I start off by saying, I've made plenty of mistakes myself, because science is a human endeavor. We all make mistakes. Now, if we own up to it, we discover them soon enough, we often have a way to recover from it. But if we do not know, then we can't. I got burned very early on my career. I'd put out an experiment at one of our stations. This was at Auburn. Got the data back. I couldn't plan the trial, so I gave them the randomization. The packets were all labeled properly. And I got the data back, and it didn't make any sense. Nothing. I mean, yeah, we get some unexpected results, but this made no sense at all. And I kept asking, and I think it took me about 2 months till they finally owned up. Yeah, we made a mistake in planting. We mixed up some samples, but we don't know what happened. In other words, the trial was done. They shouldn't even have taken data. Now, that's one thing you don't want to happen. So, experimental unit mentioned already, it's the smallest unit to which it applied, and the experimental error is that treatment line. If you are clear about those definitions, you don't have any problem. And then this will result in a scale, what I call a scale appropriate error term. If you are trying to estimate differences on the farm level, then your experimental unit is the farm. It is not the 20-foot row of corn or soybeans on that farm. And that's why when you have, for example, a strip block design, you actually have 3 different experimental units, and because you have the main plot unit 1 in one direction, main plot unit 2, and the interaction plot. So you have 3 different size experimental units, and even if they're not in different sizes, the top one, they will have different orientation. And then the subplot error. So this is a problem that people do when they're doing experiment at 3 locations and then they're trying to compare the locations. You can't, because location itself is not replicated. How can you get this? Well, do the experiment another year. Well, of course you can't replicate years anyway. So years is a replication fact. You can't, because years are not but it doesn't make any sense because no 2 years are the same. And then sampling unit, so it's when you take more than one observation on a unit, but do the analysis at the experimental unit. Treatment designs, we have factors, and then we have levels. It's a specific state of a factor. So when we have a lot of trials of factorials, so we have all combinations of the factors present at a given time. For example, a 2 by 2 factorial or 2 squared factorial. Often we have what's called an augmented factorial, where we have a true factorial plus another augmentation, maybe a standard design. Classical example, the no-treated control in weed science. It's really not of interest, but you need it in weed science research to show that you actually have the weed pressure. Now, if you don't have the weed pressure, all your herbicide treatments or whatever you do, they're really highly effective because you didn't have any weeds. Now, you may need more than one in weed science experiment because of the spatial nature of weed. Then we have treatment design. So if we expressed, for example, the rate in herbicides is in terms of gram of active ingredient per unit area, then we have a nested design because by definition, unless you have the same class, the same formulation, they will be different. I mentioned this already, analyze them as you randomize them. So the analysis that's being conducted should reflect that. Big thing is interactions. The reason we do agronomic experiments is because interactions is where the story is. It also scares people. It helps to remember the classic definition of an interaction. Interaction happens when the differences between 2 levels of one factor are not the same at all levels of the other factor. Very simple. You have in a 2 by 2, and that's what we use because it's easy to see. We could have simply a magnitude effect. Now, if you are a plant breeder and looking at yield, I don't care. I pick this entry because it's the best at all locations. I don't need statistics. I pick the best one. Now, however, in agronomic research, this, and even if it's steeper, this implies that the compound or whatever you do is more has a higher effectiveness at one location than it might have the other. So agronomically, it's important. However, if you were to conclude in your sales pitch, now this particular compound does well across all locations that we tested, you wouldn't be wrong, but you're probably missing part of the story. Now, this is a problem if you have a crossover. So the best treatment at level A1 is actually the worst treatment at level A2. This is where if you drew an average here, you would conclude there is no effect. And a lot of people make the mistake. They're saying, well, if you don't have an interaction effect, your main effects, or if main effects are not significant, your interactions don't matter. Well, no, because they are orthogonal, they are independent. Knowing something about the main effect doesn't tell you anything about the interaction effect. Most often we have a situation like this, that we have a magnitude effect and a crossover effect combined. Now this is where you really helps when you plot your means, and you may discover, well, here, yeah, it looks like an interaction, but it's essentially the same. If you would calculate 95% confidence intervals for those two means, they would overlap almost completely. So you can basically argue at this level. But interactions and the approaches, if you do it, the bottom-up approach. So you deal with the interactions first, and then and I love interactions, but then again, I'm weird. Now, dealing with this is a recent client. They were using material that they sampled from a peanut trial, a 2x2x2 factorial, RCB3, and it was actually a split plot in time. Or some of you may prefer the term repeated measures. It depends on the residual covariance structure. So they did a gene expression experiment, and they conducted as a CRD, and they basically treated each one and treated it as a CRD, each sample. But the underlying field experiment is the proper basis for this analysis. The problem that you have here is that you have very low degrees of freedom for your error term. Now this is the first one. We are actually in the process now and to see if actually these various error terms that we have, and we had 3, whether or not they are homogeneous. There's some work by Sam Carmer, former long-time experiment station statistician at Illinois during the 60s, 70s, and 80s, that gives some ground rules what you can do to pool these variances. But that's the problem that we often run into, and this is an ultimate low number, small number experiments, and that's where you're always going to run that into that. So how to conduct a better experiment? First of all, you want to plan to succeed. Failure is not an option. Or to belabor, one of the things is failing to plan is plan to fail. What you want to do is we want to be able to detect differences that are biologically meaningful. I may be able to detect 1 bushel per acre difference in corn yield. I'm sorry, folks. Missing 1 row in a cornfield is probably gives you larger error than that. Proper replication, and this includes environmental replication. Particularly, no matter what compound, do you do herbicides? If biologicals, you want to test them over a large number of locations. Of course, if you don't expect to use your biologics in Hawaii, Hawaii may be a nice business trip, but it may not make much business sense or testing sense if you don't expect your product to sell your product in Hawaii. So it's of course within the target environment. Blocking is very important because we are dealing with variations in space. And in field research, we have to assume that there is variation. In fact, one of the driving forces behind mixed models analysis and the development of that analysis in agronomic research enabled us to get away from the assumption that the plots within a block are independent. And they were not independent because we created the blocks precisely because we wanted differences among blocks, so they were more uniform than they would have been in the general area. But also in time. Yes?
Can I ask you a question about blocking? If I just heard correctly, you said you have to assume that you need to block in space. Is that's in the absence of any soil data or anything? You would still advise to run a strip or
I would never assume homogeneity in field experiments.
But if you don't know it,
if you don't know it, your best line of defense would be square blocks. And the reason is because the average distance between two random points is minimal. You can draw this out. You can do a little experiment yourself. So long as you as soon as you deviate from that square arrangement, the average distance increases. Now, it's often not possible to make perfectly square experiment, but it's an approximation anyway.
Because I've often seen field trials, we've run them where you've had maybe 10 treatments lined up in 4 blocks like this. And in the absence of any real clear data as to why you would need to do that, do you run any risks that you would be better off? Could
Yes.
the claim be made that you would be better off just
Yes,
randomizing
it's
everything?
experimental design. This a blocked experiment is like an insurance policy. You know, when you take out life insurance, of course, you have the expectation that you will survive. However, if you do not, at least your family is protected. But you pay the price. You pay that premium. And that's what we were talking. You were talking about the health insurance last night. He said they have been going on without health insurance for time because they made the decision. Health insurance was so expensive, and they rolled the dice. And it worked for 1 year, but sooner or later it's going to catch up. Same deal with going from a randomized complete block from a completely randomized design to a randomized complete block design. You're using this R-1 degree of freedom, and you're hoping that the variation among blocks, that's a reduction that will be pulled out of the residual term. So that's what you're hoping for, but there's no assurance there. Yeah, it's in many cases it's like an insurance. You always pay the premium, but you may not collect. If you're doing a response curve, you have to have enough treatments that you can actually estimate the shape of the curve. If you have only 2 points, every relationship is linear. You don't know what's going on. If you have 3 points, then you can estimate the linear relationship and the deviation from linearity. It's not quadratic because you don't know the higher dimensions. If you have 4 points, you can actually estimate linear and quadratic component if it's a linear type problem. So you have to have more levels than that. And if you had a choice between more replicates for each level and more levels, choose more levels. You're better off in the modeling realm there. Often overlooked is careful experimentation. And that's used to be experimental design and planning was really very important in the 60s and 70s because you had to always worry about, can I analyze the experiment? And then analysis became very easy and sloppiness increased. And I just say, statistical errors add up, they don't cancel out. Because remember, variances are quadratic terms. So even a negative deviation, you square it, it adds up. And there's simple things. For example, if you had a plot trial, you measure yield, is that you actually know the harvested area. There's a lot of little things that you can do. Calibrating, if you use a yield monitor in a field experiment, you've got to make sure that actually the yield monitor records the yield correctly. So there's a lot of little things you can do, or if there's post-harvest processing, and the processing is possibly done by different people. Now, do they have the same care? Do they even weighing samples? Are they in fact have the same care? I've worked over my career with a lot of undergraduates, and I made a few observations in that people who need the money to go to school actually are more careful than people who just earn some extra spending money. Also made the observations that females are usually much more careful experimenters than any southern male students. I have to qualify this southern male. Yeah. No, it's and all the influences. You just need to know. So you block it. I did a lot of forage analysis. So the grinding, we have to grind that, and that's not a precise process. and so other people who are doing it are actually put the care in. So if you're not sure, block the experiment so they can say, okay, this is these samples processed on Monday. They come back from a long weekend, and maybe it was hunting season, whatever it is. And if you block by day, then then that block information, that error due to blocking to time of the week or day of the week, will be subsumed in the block term and removed from the residual terms, and you're still clear because all the comparisons you're making are within blocks and then averaged. So I'm basically at the end. What I've given you is some nice stuff to read. This is my former advisor, Mike Kassler. Wilfred Vimeris is at UF, they're biomass people, and Richard Dixon used to be at the Noble Foundation in Ardmore, Oklahoma. He is now at University of North Texas. Yeah, he is a really top-notch molecular biologist. But anyway, they are all editors of bioenergy research, and they saw a lot of problems. So they decided that they were going to write an article of replication concept, and that's basically the guideline by which to evaluate experiments. I happen to be the external editor for this because obviously they couldn't edit their own stuff. That wouldn't be cool. This is a really good article, Fundamentals of Experimental Design. This was part of a Agronomy Society symposium in 2012. And in terms of interaction, this is a nice little article, quite dated, but the message is there. And then from Hans-Peter Pifo's group at Stuttgart-Hohenheim for the analysis of mixed models, because that's really what we're doing. We're not using general fixed effects models anymore. Most of our experiments are of a mixed effects model. And then if you want in your personal library, this one, yeah, I like Hitchhiker's Guide. So I think the answer is 42. So, but Stephen is a corn breeder up at Guelph, and he developed this little book for his students, and it's I really like it, and it's really practical. It's not high powered. It is for the practitioner. And you have to write him. You can find it online, but he self-published it. So this is my little spiel about experiments and questions. Yes.
Is there? I've seen agronomists many times.
Yeah, just watch. Just use that.
I've seen agronomists present data many times, and for some reason, most of the time I see them do percentage of change on means. Is there a standard of why that's done by a lot of agronomists? They don't show standard error bars on their graphical. They will show a percentage, say, between control and treatment. It's
not any paper
I've seen it. No, like when they present data.
Yeah.
They do that.
Well,
many
in
times.
in a presentation, you often do that because it's easier to digest. If I say, okay, rather than saying, well, I have a 2 bushel per acre yield. So, don't know, but if I say that yield is a 20, let's assume I'm making up numbers, a 20% difference. Yeah, that's a big deal. It's an effect size. Now, in the paper, then, when you actually write it up, you do the actual difference and accompanied by a measure of dispersion. There's any mean that is presented anywhere should be accompanied by a measure of variation that's associated with that mean. Otherwise, it's meaningless. I mean, just the example that he mentioned this morning. Yeah, well, 90 minutes less sleep in a day may sound a big, but what if his standard deviation was also 90? That's what the number may be big. But if you put it in relation to the variance that's associated by it, may not be. Just because you can drive a truck through it, doesn't mean it's meaningful. Yes.
I can just comment on your comment. We use that technique as a normalization technique So you can look across a variety of experiments.
Yeah.
From a normalization standpoint, you can get a perspective of where they fall relatively.
Yeah.
So it's not a direct mean comparison, but it's a relative perspective on how a product is performing.
Yeah, and you can actually do that if you do trials at several locations, and one location may have drought. You may be under dryland conditions, so your yields are compressed. So you don't see any difference, but you normalize it by expressing it, let's say, to the zero control or whatever you pick as your control, and thus the data become comparable across locations.